What topics are possibly on exam 1 for Calc 2? Calc 2 exam 1. Explicit topics that we've had homework on starting in chapter 7, but of course, things from chapter 5 and 6 should still be able to be used if you need it. For example, average value of a function or something like that. For Calc 2 exam 1, we started in chapter 7 with substitution. The first question that might come up in your mind about, well, any integration technique, substitution, integration by parts, partial fractions, is, could there be gateway type questions? Answer, yes, there could be, even though the gateway is done for most people. But do still review how to do basic kinds of integrals. Don't put every memorized integral on your note card. It's not worth it. Okay, do spend some time memorizing integrals too. And you should be able to use substitution for definite integrals, as well as indefinite integrals. And you should know the theoretical form for why it works. Let's review that quick. In general, you use substitution when you're integrating the product of two functions, one of which is a composition, and the other of which is the derivative of the inside function. Sometimes it's some modification of this a little bit that might involve a constant as well that's being multiplied. But this is the essence of the situation where you use substitution. What substitution? You'd let W be g of x. And then dw would be g prime of x dx. If I assumed capital F is an antiderivative of little f, assume capital F prime equals little f, and use the FTC and the chain rule, I could rewrite this integral without an integral sign, with a little bit of guesswork, to be capital F of g of x evaluated from x goes from a to b. In other words, do capital F of g of b minus capital F of g of a. If I assume capital F is an antiderivative of little f, in other words, capital F prime at any input value equals little f at that same input value, use the FTC and the chain rule, I can say this is true. Why? Because the derivative with respect to x of capital F of g of x would be, by the chain rule, the derivative of the outside function, plug in the inside function, multiply times the derivative of the inside function. But I'm assuming the derivative of the outside function, capital F prime, is little f. So I get the exact same function based on that assumption as what I'm trying to integrate. But why does this equal some other integral where I change the limits of integration? And what would that other integral be? Still got to equal this. What's another integral equal to that? Using the fact that capital F prime equals little f. How about just a plain old integral of little f from g of a to g of b? And what should I call the variable? We've usually called it w. Though I could use some other letter. I could even use an x. We did this before, a couple weeks ago even, maybe. Went through this derivation. You should know this derivation for the test. Will I ask you to redo it? Probably not in full, but maybe ask you reasons for things. I'd say this equation is true. Tell me why. I just briefly said why in this situation. And then you should be able to apply it for particular definite integrals. And I do want to see you change the limits of integration if you want to get credit. Full credit, at least. Yes, two wrongs can sometimes make a right in this context, but I don't want to see that. This is a situation where I am picky about details. Because it's worthwhile, because if you've got to take multivariable calculus, And you got to use polar coordinates to do a double integral. If you don't get in the habit of changing limits of integration now, you'll be in big trouble then. Next technique was integration by parts, which you should be able to apply to do indefinite integrals. Our textbook writes it like this. The integral of u times v prime is u times v minus the integral of v times u prime, where u and v both depend on x. As far as actual integrals to do, the integrand function, you should first pick v prime to be something easy to integrate to find v. Then let u be the other thing. And hopefully u is also something whose derivative is simpler. You want this integral over here to be simpler. If you used another textbook in your past, you may have seen it written like this. And this is fine as well. Though once again, everything ultimately depends on x. If our textbook is the only one you've ever used, just use that form, just so you don't get confused. You should be able to answer why integration by parts works for definite integrals as well. And then with definite integrals, you do not change the limits of integration with integration by parts. Let me put the dependence on x in here. You get u of x times v of x evaluated from a to b minus the integral of v of x times u prime of x from a to b as well. You do not change the limits of integration when you use parts. Why does this work? It's equivalent to another equation that you can obtain by, first of all, adding this integral to both sides to cancel it on the right, and get this integral plus this integral on the left. And then using a property of integrals that the sum of two integrals over the same interval from a to b is the single integral of their sum. In other words, you could write this. That's the integral that I get when I add this integral to both sides, and then use a property of integrals on the left. I'm claiming that these two things are equal. But why would that be the case? Am I using the FTC here? Is that an antiderivative of this? The answer is yes, by the product rule. Substitution reverses the chain rule. Integration by parts reverses the product rule. Product rule says that the derivative with respect to x of the product u of x times v of x, a left function times a right function, is left d right plus right d left. Exactly the function that's being integrated there. So this u of x times v of x is an antiderivative of the function I'm integrating. By the FTC, the integral will equal this, which does equal u of b times v of b minus u of a times v of a. And then rearranging gives you this one, going backwards. That's why this works. And again, not that I'm going to have you derive this from scratch, but if I asked you for a reason why these two things are equal, for example, I should say it's because of the product rule in the FTC. Section 7.3 was about tables of integrals, as well as some trickier substitution problems. Help you use a table of integrals. Will I ask you a table of integrals problem on the test? Not likely, but I'm not completely ruling it out. Probably the most important kind of table of integral problems for me, in my mind, is integrating cosine of some number times x times sine of some other number times x. Reason being is these kinds of integrals come up all the time in many applications, the most prominent of which is Fourier analysis, to come up with Fourier series. which is really important in modeling physical phenomena. Signal processing is all about using Fourier analysis. And, you know, you don't have to try copying the table, or any table for that matter, of integrals. If you needed some line from a table of integrals on the test, I'd probably just give it to you, okay? Just to see, do you know how to use it? 7.4 was about both partial fractions and trig substitutions. It's kind of incredible to me that they tried to fit both subjects into one section, but they did. We covered this over like at least 2 days, maybe 3 days of class, parts of 3 days. Partial fractions sometimes showed up in the gateway, but without long division, not ruling out putting a long division one on the regular exam. Trig substitution, those problems are typically at least somewhat hard. You've got the somewhat hard ones and the really hard ones, like where you have to integrate secant with that crazy trick. Not going to put that really hard one on the test, but maybe a somewhat hard one. In fact, the first problem on the sample test, I think both for the PDF and the video, is a trig sub problem that's moderately difficult. Do you have to know the trig identities that are helpful? I think sometimes I've given them and sometimes I haven't. That's not the greatest answer, huh? Let me decide. Certainly you should know cos squared plus sine squared equals 1. I'll decide by tomorrow morning whether you need to know them or not. I'll write the exam by tomorrow morning. It's really worth remembering that cos squared x equals 1/2 plus 1/2 cos 2x. Catch that? Cos squared x equals 1/2 plus 1/2 cos 2x, and sine squared x equals 1/2 minus 1/2 cos 2x. There's also a double angle formula. Sine 2x is 2 sine x times cos x. We moved on to numerical integration. New topics. Going beyond the basics in chapter 5. The basics in chapter 5 was left-hand rule, right-hand rule, trapezoid rule. Trapezoid is the average of left and right. New topics, new methods included the midpoint and Simpson's rule. You should know that error in the approximation is actual value minus approximate value and be able to compute the error. You should know how errors behave. I left that somewhat up to you in doing the reading. I told you verbally how they behaved, and we looked at examples. But I also said you want to look at the reading to get that carefully and problem solve. And I think on the sample exam in the video, I think I do an example. Like what happens to the errors if you multiply n by a factor of 10, for example, in all the rules? How do the errors change? How do they go down? What does the sign of the error mean? In which situations are the different rules overestimates or underestimates? And what does that mean about the sign, positive or negative, for the errors? Left and right are related to whether it's increasing or decreasing. Trap and mid are related to whether it's concave down or concave up. Simpsons, we didn't really say what the sign of the error was in terms of the behavior of the graph. In fact, it's more complicated. It's related to the fourth derivative instead of the first or second derivative, which you can't really visualize so easily. We moved on from there to improper integrals. And then finally, our geometry applications to both areas, volumes, and arc lengths. And all along, to some degree, we did probability and statistics application. With improper integrals, you should know how to compute them using a limit in certain simple situations. And also in still relatively simple situations, be able to use the comparison test to do a proof of convergence or divergence. Again, the geometry applications, that's the slicing idea. Setting up integrals either with Riemann sums or infinitesimal approaches. You should feel comfortable either way if I asked you to do it either way. Get the integral, do the integral, include units. Question over here.
With arguments, do you want?
I want you to understand derivations, and so I might ask for a Riemann sum and or an infinitesimal equation.
So, no,
I'm not guaranteeing. Comparison test for improper integrals.
so the arc length ones, is it okay just to use numerical integration on the calculator?
I might give you one where it's doable. And you'll see samples, I think. Like one sample problem is this number 6 right here. Can find the distance traveled function. You do not need to know about vectors. You'll see vectors in this problem. You don't need to know about vectors. In the probability problems, you should be able to compute a CDF and a probability, but you do not need to know how to do means and medians. We didn't cover that. We will later in chapter 8. You don't need to know about center of mass. I think there's a center of mass problem here somewhere. Yeah, center of mass. You don't need to know about that. We'll do that for exam 2. Areas, volumes, and arc length. It could be any axis, horizontal or vertical. Could also be where I specify the cross section to be equilateral triangle or square or a semicircle. We did the triangle example in class. Squares are actually easier. It's the triangular ones and the semicircles that are a little trickier. Yeah, I told the last class maybe. I guess I better tell you maybe as well. Basic plot or parametric plot is what I'm after. Probably not this manipulate one, because we haven't done that much, but to make a basic plot or basic parametric plot, nothing fancy. You don't have to color the graphs or anything like that, but just get the syntax for a basic plot or parametric plot down.